Hello and welcome back to Fourier Transform, the video series where we talk a lot about the special and important integral transform. And indeed, in today's part 27, we will just look at some basic calculation rules we have for this operator. More concretely, we will look what happens when we translate a function before we calculate the Fourier transform of it. However, as always, before I explain what this actually means, I first want to thank all the nice people who support this channel on Steady, here on YouTube or via other means. And as you might know, as a member on Patreon or Steady, you can access all the additional material for the videos. And then without further ado, let's immediately take the Fourier transform as our integral operator. This means that we have a linear map f that maps one function space into another. In fact, as we have discussed in the last video, the input space is given by the integrable functions and the output space by the continuous functions that vanish at infinity. So you see, the situation here is not symmetric. The functions that come out of the Fourier transform don't have to be integrable anymore. And as you might remember, we have already discussed an example of that in part 25. In the one-dimensional case, this was quite simple, because we could just consider the indicator function of the interval from -1 to +1. And the Fourier transform of that is the famous sinc function. And indeed, this is a function that fluctuates a lot, but it still goes to 0 when we go to plus or minus infinity. So this is what happens in this example, and it's the best one to see that the result does not have to be integrable anymore. So this is something you should remember. The sinc function does not lie in L1 because the absolute value has not a finite integral. In fact, this is not so hard to show, because in the end you just have to sum up all these parts and you can estimate this with the harmonic series. So you get out infinity for this integral. However, this should also give you the idea that if you include the signs in the integral, then the whole integral should have a finite value. So if you don't have the absolute value involved, we can calculate this integral for every lambda, and in the limit lambda to infinity, this one is actually pi. This is also an interesting fact, but the important result for us here is that we cannot apply the Fourier transform to the sinc function. Hence, applying the Fourier transform f twice in a row is usually a problem, but we will solve that later with a special subspace. However, in this video here, we will first look at all possible L1 functions, and we will see what happens when we translate the function here on the left-hand side. And what we mean by that is really easy to explain. We just take the graph of the function here and put it to the right or to the left. So here in general, you could just say that we shift by a number a. Obviously, this does not change the integral on the left at all, but it will change the resulting Fourier transform on the right. And indeed, how it changes exactly, we can just calculate by using the definition of our n-dimensional Fourier transform. This also means that we actually translate in Rn. This means we can consider any vector a in Rn. Therefore, inside the integral, we find our complex exponential function as always, and an integrable function f. However, now we know we don't have f of x because we want to shift it by the vector a. Therefore, the new function we want to integrate here is actually f of x minus a. So this is the whole translation we want to do, and now we can just calculate how the Fourier transform on the right will change. And to do that, as you can see, we just have to do a substitution. So x minus a is what we now want to call y, and you can immediately see we don't change anything in the integration here, but we will change the complex exponential function. Namely there, we just have to substitute x, which means we have y plus a. And please don't forget, this big dot here stands for the standard inner product in Rn. And the good thing is that any inner product is linear, so we can pull out the addition sign. In other words, we can just split it up into a product of two exponential functions. And since only one exponential function depends on y, we can take the other one and put it in front of the integral. And then you should see that the remaining part inside the integral is just our Fourier transform of the original function f. And this is the result we wanted to show. We see how the Fourier transform changes, namely we have such a factor in front. And if we abbreviate the Fourier transform of f by f hat, this is the resulting formula. So an additive translation in f gives us a multiplication for f hat. And in order to make this precise, we should define a translation operator and a multiplication operator. So maybe let's call the translation operator TA, and this one should act on functions defined on Rn. This means TA of f is a function defined on Rn again, but now shifted by the vector a. So if we put in a point x, we get out f of x minus a. So nothing new, but we have introduced a new name such that we can deal with these translated functions as well. And in addition, we can also define a multiplication operator, and let's call this one MA. So this one should also be a map that acts on function defined on Rn. And obviously it does not matter if we call the variable name p or x, so let's keep it simple and let's stay with x here as well. Therefore what we get here is that we multiply with the exponential function that has x and a in the inner product. And as before, this should just be a factor for the original function, which we now call f of x. Okay, and now with the help of these new two operators, we can describe the identity from before in a new shorter way. And let's simply put everything into a proposition. And as already shown, the whole formula works no matter how we translate, so we can choose an arbitrary a in Rn. And since we want to calculate the Fourier transform, we need an integrable function f. And now we can translate f by a and calculate the Fourier transform of this new function. And now we already know, if we want to pull out this TA, it becomes an MA. But most importantly, we have MA applied to f hat. So this is exactly the formula we have proven before, but this is a formulation you can easily remember. And now interestingly, this also works the other way around. This means instead of translating the function f, we could also translate our f hat in the frequency space. And to make this change a little bit clearer, I now use the letter b instead of a. So let's put this new function on the right hand side. There we have tb of f hat. So it's exactly the same definition for the translation operator, but now it acts in the frequency space. And now maybe not so surprising, it turns out that this goes to a multiplication operator for our original function f. But in contrast to before, there is also a minus sign involved. Still everything else looks the same, so if you want to pull the multiplication operator out of the hat, it becomes a translation operator. So this is definitely something you can easily remember, but you should always be aware where the minus signs are in the equations. Otherwise, I would always say it's good to have this nice mnemonic device which says that translation operators and multiplication operators exchange in the Fourier transform. And now I would say it's also helpful to see the proof of this second formula. So there the starting point is to look at this new function given by the multiplication operator, and then we want to calculate the Fourier transform of it. And then let's evaluate it at the point P. This means we just have to use the definition of the Fourier transform given as an integral operator. And then we just put the function in where we have minus b in the exponential factor in the front. And this immediately tells us that we can combine this with the other exponential function. So then we only have one exponential function, and there we find p minus b in the exponent. And this one is still in the inner product with x, and the rest does not change at all. Hence we directly recognize that this is the Fourier transform of f, just not evaluated at p, but at p minus b. So we can simply write that this is f hat at p minus b. And there we have it. This is simply the translation by the vector b. So clearly it's allowed to just formulate it as tb of f hat at the point p. And that's already it. And now we can also see why we have this sign change compared to the formula above. Eventually it just comes down to the complex exponential function here, which also implies that you have to apply the Fourier transform 4 times to get out the original translation operator again. In fact, soon we will see that for nice functions f, applying the Fourier transform 4 times will not change anything. And such a fact is really helpful if we want to describe a formula for the inverse of the Fourier transform. This would mean that we can describe the original function f by just using f hat. However, this discussion is definitely something for the next videos. So I really hope I meet you there again and have a nice day. Bye bye.